Okay, I hear the recording in progress. I will share the screen. Okay, so I'm about a day ahead. I was supposed to only start 11.4. I'm probably going to finish 11.4 today and most likely finish a little bit early. Okay, reminder, this week is a short week. We have a holiday for the 12th for Veterans Day. So that means our quiz for the week will be on the 11th. Okay. So we're doing the comparison tests, plural, 11.4. I did some last time. I'll do more, a few more, and then I'll set you up for many of the others. And then that's pretty much about it. Okay. All right, so let's go back to the comparison tests, plural, of which there are two. Right, so the text version of the comparison test is here. Okay, page 727. If you have two series with positive terms, A sub n and B sub n, or series, by the way, side note, series is singular and plural. So the plural of series is still series, it stays the same. Okay. So what does 1 and 2 basically say? It says if the bigger series converges, the smaller series converges. Okay. You are poorer than a poor person, then that means you're also poor. And number 2, if you have a divergent series, then the series that's bigger than it also diverges. You are richer than a millionaire. So if you're richer than a millionaire, you're rich. Okay, but you cannot make any statement for the other situations that I had mentioned before. Okay. Then the limit comparison test, which is actually more useful because you don't have to worry about which series is actually larger or smaller. It's just that they have to behave, quote unquote, like each other. And what does that mean? If the limit as n approaches infinity of A sub n over B sub n is a constant, then either both series converge or both diverge, which means whatever happens to one happens to the other. Okay, so we did some last time. I'll do a few more, set you up with others, and then we'll probably end it a little bit early. Okay, so some problems at the end, I think. It's 27. Summation 1 plus 1 over n squared e to the negative n. Okay, and let me just check my notes here real quickly. We'll go on. Okay. By the way, it's never wrong to write some of the terms out so you can kind of see what's going on. First, I write this as over e to the n. All right, so I plug in 1. 1 plus 1 is 2. 2 squared is 4. 4 over e. Plug in 2. 1.5 squared over e squared. Plug in 3. It's 1 1/3 squared over e cubed. Plug in 4. 1 1/4 squared over e to the 4th. Plus dot, dot, dot. Okay. So if I kind of ignore the numerators for a moment, it looks like 1 over e squared, 1 over e cubed, and so on. It's a geometric series where I keep multiplying by 1 over e. 1 over e is less than 1 in absolute value. So we think it ought to converge. But I have these weird numerators. Okay, so if we believe this thing is going to converge, if I only look at the denominators, say 1 over e squared, then the strategy is, okay, we think the series is converging. So can I come up with a bigger series, so to speak? Term by term, I've got something bigger that I know converges. Then I can use a comparison test. So look at the numerators. 4, 1.5 squared, that's like 2.25. 1 1/3 squared is what? 4 over 3 squared is 16 over 9. They're getting smaller. Okay. So a so-called bigger series term by term is summation of 4 over e to the n. And I know this converges. Therefore, this series, which is all positive and term by term less than or equal to this series, will also converge. So that's a strategy. All right, so I compare it to summation of 4 over e to the n. Okay, so if I look at this, 1 plus 1 over n squared is less than or equal to 4. You look at all the terms here. Now, if you plug in 1, you get exactly 4. 1 plus 1 is 2, 2 squared is 4. Okay, and then, after that, then the left side is going to be strictly smaller than the right side. 1.5 squared is smaller than 4, 1 and 1/3 squared, and so on. Okay, so I have 1 plus 1 over n squared is less than or equal to 4 for n equals 1 to infinity. Then I divide both sides by e to the n. So I have this relationship. 1 plus 1 over n squared over e to the n is less than or equal to 4 over e to the n. Okay, and then what do I know about summation 4 over e to the n? It converges. Why? It's a geometric series where the r is 1 over e. 1 over e is like 1 over 2.7. R is between -1 and 1. Okay, so the bigger series converges. If the bigger series converges, then the original series also converges by the comparison test. Okay. So the strategy was, I think this thing's going to converge. I can't really make heads or tails of the numerator yet. But if I ignore it temporarily, I just say, okay, what if I have 1 over e to the n? Okay, that's a geometric series which converges. So I want to force the original series to be a bigger series that I know converges. Okay, I know 4 over e to the n converges. Therefore, by CT, not LCT, regular comparison test, I know that the original series converges. Okay, so that's the analogy of we are poorer than a poor person. Okay, so if we're poorer than a poor person, we're also poor. Okay. I cannot look for a smaller series though. So suppose I said compared to 1 over e to the n. Okay, that wouldn't help because then you would be saying essentially I'm richer than a poor person. So if I have more money than a poor person, well, you still might be poor, you might be rich, you might be in between. You can't make any statement. Okay. All right, so that's the way that one works. Okay, 31. Summation n equals 1 to infinity. Sine of 1 over n. Okay. Sine of 1 over n, well, we don't know too much about that. We do kind of recognize 1 over n. That's our quote unquote famous harmonic series, which we know diverges. Okay. So why don't we just go ahead and make that comparison? Compare sine of 1 over n to 1 over n. Now, it's pretty hopeless to think about, is this one going to be bigger than this or smaller than that? So we're not going to aim for comparison tests. We'll aim for limit comparison tests. Right? I don't want to have to compute, sine of a number compared to the number itself. I don't know. So we'll just do this. Right, so limit comparison tests, you take the limit of the ratios. So limit n approaches infinity, sine of 1 over n divided by 1 over n. That's a 0 over 0 case. Plug in a super big number. This is 0. Sine of 0 is 0. So L'Hopital's rule applies. L'Hopital's rule says take the derivative of the top, derivative of the bottom. Okay, the derivative of the bottom, I'm just going to write as 1 over n prime. I could figure out what it is, but I don't have to. Yes, this is what? N to the -1. So the derivative would be negative n to the -2, but I don't really need that. Okay, because, let me just temporarily put 1 over n prime. What is the derivative of sine 1 over n? Cosine 1 over n times the derivative of 1 over n prime. And these 1 over n primes just cancel out. So I just have limit n approaches infinity of cosine 1 over n. Well, when n gets super big, that's cosine of 0, and that's 1. Okay, so the limit comparison test says these two essentially are the same for super big n. Remember, we're doing a ratio. In the limit, the ratio is 1. That's about as close to being close as you can get. Okay, so remember, if you have a fraction, a over b, and equals 1, that means a and b have to be equal, right? Here we're saying the numerator denominator approach 1 in the limit. So they're almost the same. The farther out you go, the more alike they are. So in other words, the sign of 1 over a billion is very close to 1 over a billion. Okay, so that means, according to LCT, limit comparison test, whatever happens to one happens to the other. So what happens to this one series that we know? Summation of 1 over n diverges because it's the harmonic series. Therefore, the original series also diverges by the limit comparison test, LCT. Series diverges. Okay, so, quick reminder of limit comparison test. If you believe a series behaves like another, and then we still have to prove it. To prove it, you take the limit of the ratio. And if you get any positive quantity, you stop and think about it. If it can be any positive number, there's a lot of positive numbers, right? Now, a lot of our problems, they came up to be 1, but it's allowed to be 7, 55.00001. The only things that are not allowed are 0, infinity, and does not exist. It's got to be positive because you're only comparing positive terms. Then whatever happens to one happens to the other. That's what it means by both converge or both diverge. Kind of like the integral test. If whatever happens to the integral happens to the series. If the integral converges, the series converges. If the integral diverges, the series diverges. Okay, so same thing here. Okay, if one series converges, the other converges. If one diverges, the other diverges. So I took the original series, which was a little bit harder. My comparison series was something I know about, summation 1 over n. Okay, I established the ratio in the limit was 1. It's allowed to be 2 or 5 or 80 or 0.01 or 1 over a million. Okay. Then what do I know about the one series, summation 1 over n? That diverges because it's the harmonic series. Therefore, the original series also diverges by the limit comparison test. And again, by this rule, we always have 2 series. And plural of series is still series. And you say, how do you know which one to put on top, which one on bottom? It doesn't matter. Okay? Because if one way you take the limit, it comes out to be 3. That's positive. If you go the other way, you flip it, the ratio will be 1/3. That still works. Okay? It's still not 0. It's still not infinity. And it still exists. Okay? So you can't go wrong by putting one on top of the other, let's say. Now, one way or the other might be easier to compute the limit. But if the limit comes out to be a positive number, you flip it, it's still a positive number, right? Reciprocal of a positive is positive. Okay. And if you had 0, you can't flip it anyway because you can't flip 0. And same thing with infinity. And if the limit doesn't exist, when you flip it, this limit still wouldn't exist. Okay. All right, I was only going to show you one more, and then I'll give you some hints about others, and then otherwise I'm just about done. Summation n equals 1 infinity, number 29, of 1 over n factorial. Remember the factorials we talked about? We're going to do a lot more factorials later on, so get comfortable with the factorials. So it's 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, plus 1 over 5 factorial, right? Number 2 factorial means 1 times 2. 3 factorial, 1 times 2 times 3. 4 factorial, 1 times 2 times 3 times 4. 5 factorial, 1 times 2 times 3 times 4 times 5. Okay. If you kind of just look at the numbers, it seems like it's going to converge, right? The numbers are dropping quite rapidly. But right now, I don't know, I can't make heads or tails out of this. And let's think of the test that we have. Can I do the integral test? Can I do the integral test on this? Do we know how to integrate factorials? Do you remember in Calc 1 ever integrating factorials? No, you didn't, for a very good reason. Okay, the factorials only define on whole numbers, 0, 1, 2, 3. There's no such thing as 1.5 factorial. And in Calc, Calc 1 especially, we're dealing with smooth, continuous functions and so forth, right? So we never learned how to integrate something like a factorial. Okay? Now, there actually is something that you can integrate that's sort of related to the factorial, but strictly speaking, the factorial cannot be integrated, so we can't do the integral test. Okay. So the strategy that I used here is say, well, I know summation 1 over n squared converges. How come? It's a p series with p equal to 2 less than 1. And I hope this is a bigger series than this term by term. So I wrote some of the terms out. 1 over 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, and so on, right? And then I look at these two, same. These two, and you have to watch out again. By the reciprocal rule, the larger fraction has a smaller denominator, right? Okay, so follow the logic. Here's how the factorial grows. Here's the 1 over n squared. These are the same. Here, the 1 over 2 is bigger than 1 over 4, right? If I have half a pi, that's bigger than a quarter pi. 1 over 6 is bigger than 1 over 9. But after that, 1 over 16 is bigger than 1 over 24. 1 over 25 is bigger than 1 over 120. This drops much faster, right? So we can say for n greater than 3, if I ignore the first 3 terms, if I just look at this, I'm allowed to do this, okay? If I include a finite number of terms or throw out a finite number of terms, that doesn't affect convergence or divergence. If I just decide to start at n equals 4, for n greater than 3, 1 over n squared is greater than 1 over n factorial. Okay, if I ignore these 3, this is bigger than this, right? Smaller denominator, smaller denominator. This is going to shoot way past this in denominator, so this will be larger. Right? So 1 over n squared is the larger series for n greater than or equal to 4. And I already know summation of 1 over n squared converges because it's a p series where p is equal to 2 greater than 1. So that tells me summation n equals 4 to infinity, starting with term 4 of 1 over n factorial also converges by CT, comparison test. So I know that this converges. Converge means I get a real number. Then I can go back and put in the first 3 terms. Of course, that's still going to converge. It's a real number plus a real number plus a real number plus a real number. Okay, so insert the first 3 terms. Go back and plug in the first 3 terms. Summation n equals 1 infinity of 1 over n factorial also converges. Right, so that's the proof of this one. Okay. Later on, we'll see a much easier proof. We don't know it yet. Okay, but there's going to be something down the line called the ratio test. It's much better for this. You don't have to write that down now. We'll get the ratio test pretty soon, as far as that's concerned. Okay. All right, that's as much as I was going to do there. I'm going to go back and show you in the text. I wasn't going to do any more problems unless anybody has any questions, but I'll just give you some hints for some of the other problems, and then I'm just going to be done. Okay. So the again, basic strategy for comparison test or limit comparison test is if I see the series, if I can compare, do I see something comparable? Okay. And a lot of it has to deal with what happens when n goes to infinity. When n goes to infinity, does something drop into insignificance, so to speak? Okay, now I didn't do 3, I did 3 star. Let's look at number 3. 1 over n cubed plus 8. What is insignificant in the long run? 8, right? So I would do a limit comparison test with 1 over n cubed. Essentially, it's 1 over n cubed. Remember, n is going from 1 to infinity. If I get a billion, get a billion cubed is super big, plus 8 is like nothing. So 3, I would say compared to summation 1 over n cubed. Okay, I think I did 5. 7, can you tell what's insignificant in the long run? 9 to the n over 3 plus 10 to the n. What's insignificant? 3. Remember, you're plugging in real big numbers. Plug in billion, 9 to the billion, 10 to the billion. This 3 is like nothing. So it's essentially like 9/10 to the n. Okay. 11. You kind of have to do some fractional work. So for super big N, you ignore the 4k plus 3. I'll just put in my notes here. This is k to the 1/3. This is k to the 3/2. So that would be my comparison series. And do a little bit of arithmetic to find out what happens when you divide. Looks like the common denominator would be 6. It might be a negative. So you figure that out. 13. 1 plus cosine n over e to the n. Okay, the strategy for 13 is kind of like what we did before. Just look at the e to the n. You'd have 1 over e squared, 1 over e cubed, 1 over e to the 4th. Okay, that's a convergent geometric series. Common ratio is 1 over e. So that means I'm looking for a bigger series. Bigger series, cosine stuck between -1 and 1. So the maximum this would ever be is 2. Right? So a good comparison series would be 2 over e to the n. This would be a bigger series which converges. That's my hint for that one. Okay. 15. What can you ignore in the long run? -2. So just pretend it's not there. Your comparison series would be summation of 4 to the n plus 1 divided by 3 to the n. Okay, 17, I think I did, but 17, ignore the 1 under the radical. I would compare it to 1 over n, our harmonic series, right? For 17, just ignore this, and then 1 over n. 19, hold it like this. Right? For super big n, look at this, n over n cubed. N over n cubed is 1 over n squared. So comparison for 19, I can write that down. So compare it to summation 1 over n squared, like that, for 19. Sorry, it's not straight because the book is up against the arm of the projector here, so I can't make it straight. So that's a basic game that you play for most of these. 21. Ignore the 1, ignore the 2. Right? Think of it as radical n over n and simplify that. 23, well, I would say multiply out the bottom. It's going to be n to the 4th plus blah, 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 right? So it's essentially n on top, n to the 4th on the bottom, and then go from there. Okay. 25, can you tell what drops into insignificance? Ones, right? Forget the ones. E to the n divided by n e to the n, that's like 1 over n. So compare it to the harmonic series, 1 over n. Okay, 27 we did, 29 we did, 31 we did. That's it, folks. Pretty much done. Okay, so I'm actually finished for today. I'll just tell you where we're headed, and then if you have any questions, you can bring them up. Otherwise, we're going to end in a couple of minutes. I'm going to knock off this from the list. So I'm going to declare I'm finished with 11.4. And so again, I'm still a day ahead. Okay, and we have 11.5 coming up, which is on alternating series. And so I wasn't supposed to start it until Thursday, but it's only Tuesday, and I'll just say a little bit about the alternating series test. Then I'm going to quit. So alternating series on page 732. We've already talked before about the concept of an alternating series. Okay. Alternates positive and negative. 1 minus a half plus a third minus a fourth, and so on, right? Negative a half plus 2/3 minus 3/4, and so on. Okay. So you could start with either a positive or a negative. And a common way to tell you have an alternating series is when you have -1 to an exponent. That's not the only way to do it, but that's a major way. -1 to the n minus 1 or -1 to the n. Okay, I don't really like n minus 1 as much as n plus 1. It's the same thing. If I plug in 1, -1 to the 1 minus 1 is -1 to the 0, that's 1. So the first term will be positive. So this is a technique to make the first term start with a positive. So positive, negative, alternating, right? If I go like this, start at n equals 1, -1 to the 1 is -1 times this, so it's going to go negative, positive, negative, right? Minus, plus, minus, plus. By the way, later on, we're going to start often with n equals 0. If I start with n equals 0, then I would just do -1 to the n if I wanted the first term positive. Okay. All right, here is the alternating series test on page 732. This is the book's version. I'll give you my version. Okay. So basically, you have an alternating series. Okay. And then what else has to be true? B sub n plus 1 less than or equal to B sub n for all n. That means the terms get smaller in absolute value. You get smaller and smaller, and they approach 0. Then the series is convergent by the alternating series test. Okay. Now, I don't feel like writing alternating series tests, so you know the way that I work things out. Make an abbreviation. How about AST? Okay, so AST will mean alternating series test for us. Okay, so that's the book's version. I'll give you my version and how you can write it. Alternating series test, AST. Ignore any dates, of course. If a series is alternating, which I'll abbreviate with alt, absolute value of A sub n is decreasing, arrow down. That means the terms decrease in absolute value. Absolute value of the terms gets smaller, and the A sub n's approach 0. So here's a shortcut for what do you write for me on quiz, test, homework. Just write alt for alternating. Absolute value of A sub n is decreasing, arrow down means decreasing, and A sub n's approach 0. Then the series converges by the alternating series test. Okay, so if these 3 hypotheses are satisfied, series is alternating. So clearly, you know, if you don't see the series as alternating, you can't use the alternating series test. Kind of obvious. It's got to be alternating. The terms get smaller in absolute value. Terms decrease in absolute value, and they approach 0. Has to be absolute value. Okay, and there's a good reason for that. If you don't have the absolute value, well, it's just going to bounce back and forth, right? I mean, anytime you go plus, minus, when you go from a plus to a minus, it decreases. And when you go from a minus to a plus, it increases. So if it's alternating, it's going to keep going up, down, right? So the idea is if you look at the absolute value of all the terms, okay, absolute value of all the terms are decreasing. And in A sub n approaches 0. Okay. I'll just show you quickly a plausibility argument. This doesn't qualify as a proof. It's a plausibility argument. Okay. So we're bouncing back and forth. They got B1, B2, B3. Okay. These are the terms. So the idea of alternating is you go left, right, right. You keep going back and forth. But the terms are decreasing in absolute value. So the amount that you go back the other way is not as much as when you did the previous one, right? So you go this way, then you go backwards, but not as much. Then you turn around again, but not as much. Then you turn around again, it's not as much, right? So you keep going like this. And these terms approach zero. So when they approach zero, sooner or later, you're going to converge down to a single number, which I decided to call S. A lot of times I think of an old pendulum. Okay, think of a pendulum, swings back and forth like that. Then it comes back the other way, but when it comes back the other way, it doesn't come back as far, right? Then it comes back the other way, not as far, and not as far, and not as far. Okay, and then eventually, of course, we know it converges down to a single point right here, or like some of those old-fashioned grandfather clocks. Okay, it just keeps all the way. But if you didn't let it connect and just let it free flow by gravity, then it would go like so and come back not as far, and then go back the other way, not as far, and the other way, and it'll eventually, slow down to a vertical spot right there. So that's the idea behind the alternating series test. It's alternating, right? Plus, minus, plus, minus, plus, minus, decreasing in absolute value. So when you turn around and go back the other way, you don't go as much, and the individual terms approach zero. Okay, so you have to eventually converge down to a particular number. Okay. All right, so that's the essence of the alternating series test, which I will start tomorrow. Okay, but otherwise I'm done for today, folks. So let me stop the share and see if anybody has any question. Otherwise, that'll be it. Okay, any questions? All right, have a good day. We'll see you next time. Okay,
All right,
bye.
take care, Professor.
Okay, thank you. Bye.